Good morning, good afternoon, and good evening. Thank you for joining us for Burned Out from Burning Out minus 80 degrees Celsius ULT Freezers. Get ready to have what you think you know about freezing drug product or drug substance turned on its head. I'm Amy Washko, your event facilitator and marketing leader for the Life Science Solutions Division of Trane Technologies. All attendees have been placed in listen-only mode. If you have technical difficulties, please send a message in the chat box and the moderator will attempt to troubleshoot your issue. During this presentation, you'll have the opportunity to ask our speakers questions using the chat box. Once the presentation has concluded, our speakers will be answering your questions live in a session moderated by Scott Masella, Trane Technologies Life Science Solutions Global Portfolio Manager. Let me share a little background on our presenters today. Jeff Johnson is president of Biotech Design LLC, a bioprocess engineering consultancy. Previously, he was responsible for the assessment of new manufacturing technology for Merck's vaccine, biologics, and sterile manufacturing processes. He co-led SUN, S-U-N, Merck's single-use technology initiative and the Process Technology Innovation Community of Practice. Sylvain Riendo serves as FARRAR Scientific's VP of Business Development. He began his career in the early 80s, focused on specialized refrigeration application within Carmichael Engineering in Canada. In 1988, Sylvain relocated to the United States and continued his career with Forma Thermo, where he was responsible for international distributors in Europe and APAC as a Cascade Services training specialist and later a business development manager. Sylvain founded and led Elpro Services based in Switzerland. Now I'll turn our presentation over to Sylvain.
Good morning or afternoon, everyone, and thank you for the privilege of your time today. My name is Sylvain Riendo, and I'm actually excited to be here and assist Jeff with the technical service experience that I have related to minus 80 degrees C freezers. Next slide, please. So our agenda for the webinar will focus on the following. We go into the industry freezing challenges. So this is where we go into the existing practices for freezing product using ULT freezer. It'll be interesting to see just how much energy or heat removal a ULT freezer is capable of removing. And Jeff will share the scientific data in just a few minutes. Then we'll go into the current equipment capabilities. This is where we will take a closer look at the energy required to freeze product and the limitations of minus 80 ULT freezers. I'm sure most of you are using minus 80 freezers for the storage of small samples like 2 ml vials, but are these minus 80 freezers truly capable of freezing large amount of products such as 10-liter carboys? And is the process repeatable using standard minus 80 ULC freezers? And lastly, we will discuss a better way to freeze. Be ready to be amazed here because this is where the data speaks for itself. Jeff will share data of how much energy a 10-liter carboy holds and how fast the energy can be removed. So this will be very exciting. Next slide, please. Okay, now for the fun part. This is an interactive part. This is where we would like for you to provide us with your response. We created this poll to understand your pinch point when using ULT freezer. So this poll will actually be open for approximately 1 minute in order for everyone to select their answers. We will then provide the overall data of this poll in just a few minutes. So as you can see from the poll, you can select reliability, cost, footprint, thaw, a freeze-thaw process, and material handling. And again, this is something where you know your process, you have a good understanding of where you have some of the challenges. So please go ahead and start completing the poll so that way there we can have a good turnout of like, okay, this is the average or this is where it seems to be a pinch point for several people. And in the meantime, I'm going to go ahead and ask to go to the next slide. Well, no, I'll wait. I'm sorry. I'll wait till we get done. And then with this poll, and then we'll move on to the next slide. On the, and again, the areas, especially when we talk about reliability, this is where, where we have freezers that are used for the wrong process, and then the life of the freezer is, greatly reduced, because again, ULT freezers are not designed to remove a large amount of energy. And is the cost, because then the overall cost to replace equipment or to add more equipment in order to fulfill the process of freezing bulk product, that could be quite expensive. And then you get into the footprint, right? So yeah, so looks like the challenge, so it looks like 65% appears to be reliability issues, and cost is only 3%. The footprint is 10%, although the footprint becomes quite large when you start talking several minus 80 degrees C freezer. Freeze thaw process, this is an interesting one, because unlike a ULT freezer can only do one thing, and that's to store product at minus 80. And in a control rate chamber, it's designed to freeze or thaw product, and then the material handling. And this is something that I'm sure requires a lot more discussion, because this is where, instead of manually loading several bottles into a freezer, there has to be a better way, and we'll go into the details of that. So on this slide, now we get into, okay, so what's so scientific about minus 80 freezers? This is an interesting question, and most of you may already know the answer, but generally speaking, minus 80 freezers were created to replace dry ice. So allow me to explain this a little more. So prior to ULT freezers, samples were stored in dry ice, and because the challenge with dry ice is it evaporates constantly, so you had to manually reload the dry ice onto the product. And as you can imagine, this replenishing of dry ice is labor intensive. This is where minus 80 freezers became more and more popular in the industry. Now keep in mind, the main purpose of the ULT freezer is to maintain minus 80 temperature and not to freeze warm product from ambient down to minus 80. Okay, we could all agree that minus 80 ULT freezers can freeze a few 2 ml vials to minus 80. But the ULTs were mainly engineered and designed to hold minus 80 storage temperature, since the total amount of energy removal of a ULT freezer is very limited. And again, this is where Jeff will go into the details here in a few minutes. Next slide, please. So let's take a look at why minus 80 freezers were designed to store what we call already frozen material. Jeff will go over the thermodynamics, what it takes for a ULT freezer to remove energy from a container placed within the freezer. And it's going to be interesting because, again, the data speaks for itself. So I will now turn it over to Jeff and let him take over the presentation.
Great. Thank you, Sylvain. And, I've come out of industry. I was with large operating companies, and I certainly have seen lots of upright freezers and stored lots of material at minus 80. I was always curious where minus 80 came from, because the glass transition temperature of many of our formulations are minus 30-ish. And so what's so magic about minus 80? And I found it interesting that it was actually just the temperature of dry ice, and it really has nothing to do with what's required for our products. And the uprights, these ULT freezers, were designed to replace a cooler filled with dry ice. So I found that was an interesting background. So I also heard that these were not designed for freezing, but I know some companies do use them for freezing. And so I was always curious about, what is that limitation? And so I've gone through, with the help of the team here, the calculations to really understand what these freezers can do, and then show there is a better solution out there. Next. So to do that, let's do some background. One thing to keep in mind is at minus 80, this is different than our standard refrigerators and freezers that we're used to, where it's 2 to 8 or minus 20. Here, the driving force for heat transfer is over 100 degrees C or 100 degrees Kelvin, right? You have ambient 20 to 25 degrees. The chamber is -80. Again, over 100 degrees C is a driving force. Now, there are three ways that heat's transfer. The first is the outside convection, the air, the warm air taking or transferring heat into the refrigerator. The second is the insulation, the transfer, the conductive heat transfer through the wall, through the foam. And then the third is the convection, the air transfer at the wall into the -80 chamber. Now, in these freezers, because that insulation is so good and so thick, that is by far the largest resistance. It's an order of magnitude larger. And so in our first analysis, we're only going to look at that one term. So Amy, next. So if we look at this again a little more scientifically, you can see how we show the temperature. You have 25, and then we have these three different resistances I talked about, right? The outside convection, the inside, the wall conduction, and the inside convection to get to the -80 on the inside. For this analysis, initially, we're only going to look at that insulation because it is by far the largest resistance. And the formula here for conduction is heat transfer Q is equal to the conductive heat transfer coefficient times the area times the temperature driving force divided by the thickness of the insulation. And I have the terms shown below. The heat transfer coefficient, conductive heat transfer coefficient of 0.02, that's a very, very small number. And that's because the foam used in this is a very effective insulator. The area we have calculated for the size of a standard upright, which is also the same size as the FARRAR custom designed Series 4100 rate chamber, which we'll also show, but roughly the same areas. The delta T, as we said, was 105 degrees C, which is also 105 Kelvin. And the thickness we're going to use in this initial calculation is 5 inches of foam, which is what is used in the FARRAR machine. Now, in an upright, it's 1 inch of backing panels and a couple inches of insulation, but it comes up with just about exactly the same insulating properties. And so if you put the numbers in, we come up with 104 watts. And then we've also calculated how much heat goes through the door, same calculation, different area, and we come up with 30 watts. And then there is also some heat transfer across the gasket. The gasket is a bit of a weak point, and from experience, that is 24 watts. So if we add these up, we come up with 158 watts, which is, like an old incandescent light bulb is 100 watts. This is the amount of energy that is being transferred from the outside through the insulation into the chamber. This is the amount of energy that the refrigeration system needs to be able to handle just to maintain that delta T, keep the chamber at -80. Next. So if we look at the standard upright ULT freezers, they are designed, of course, to do this, and then they have a little bit of a buffer. They have a little bit of a duty cycle so that they can handle opening the door, shutting the door, putting in samples, freezing small amount of liquids. And we got a lot of experience in this industry over the years by many people on the team. And what has been used historically in the industry is about a 65 to 75% duty cycle. And so if we take the 158 watts and we divide it by that 65 to 75%, we come up with 210 to 243 watts. So you take that minus the 158 required just to maintain the temperature, and we see that this buffer is on the order of 50 to 85 watts. And that buffer is what's left to handle the door opening and closing, and also to freeze product. Next. So let's look at the exact same thing, but this is for the FARRAR 4100 series rate freezer, which is a much bigger machine. It's what I call a blast freezer because it has convection, right? It blows the cold air across. It's custom designed for freezing. So this machine, because the chamber is roughly the same size as an upright, it's the same 158 watts to maintain the delta T. However, there is an additional energy load here because it has that blower, right? It's blowing the air across. That's additional energy that has to be taken out. And that's 325 watts. So this machine has to take out a lot more energy, almost 500 watts. However, the big difference is the design load is 2100 watts. It has a much bigger refrigeration system, a much larger industrial robust refrigeration system that can handle 2100 watts, which leaves 1600 watts as that buffer, which is 18 times more that of an upright freezer. So that sounds good, but I wanted to put that into context. What does that really mean for us in the industry who's trying to freeze product, right? So we have a couple of examples. Next. Now, to do this, just as an example, I'm going to focus in on a 10-liter carboy filled with 8 liters of product. I know many people in the industry use these 10-liter carboys. We also use 2-liter carboys. You might use Celsius bags. You might use CryoVault. There's lots of different containers. And if you have any questions about your particular situation, feel free to follow up after this webinar with FARRAR Train, and we'll be very happy to work with you to figure out your particular case. But I think this is a good example of just focusing in for now on 8 liters of liquid. So to do this, there are 3 steps in the freezing process. First, you have to take the liquid and take it from ambient down to 0. And that's about, if you look at the upper left corner and the blue, the first bullet, that's 734 kilojoules of energy that has to be removed. Then there's the big one, which is that phase change, changing the liquid to solid ice. And we're using water, but most of our products are substantially water, and I think it's a very good example for this. And that phase change is around 2700 watts. And then finally, once it's all solid and frozen, you have to take that solid down to -80, and that turns out to be 1300 watts, or kilojoules, I'm sorry. So you add all these kilojoules up and you come up with 4.7 million joules that have to be taken out. So what does 4.7 million joules mean? How can we relate to that? Well, as a simple theoretical calculation, what we've done here is the minimum time. So if these freezers were able to take out the energy linearly, very efficiently, it would give us a theoretical minimum time. In actuality, it will be greater than this. But the second bullet down in the lower left shows that for the standard ULT freezers with the 52 to 85 watts of buffer capacity left for freezing, it will take on the order of 15 to 25 hours to freeze 8 liters of liquid. If we look at this for the FARRAR 4100 series rate freezer, you do the same math, you come up with less than an hour. So again, a dramatic difference in how fast you can freeze it using this, this approach of minimum freeze time. Then we have a second example. So next. And this one, again, is a little more theoretical. And this is around the heat transfer rate. How fast can you take heat out of a carboy? And so if you remember the 3 different terms we talked about, since there is no insulation on a carboy, right? There's just that thin layer of plastic, which does not have a lot of resistance. In this case, the biggest resistance is that air transfer between the air in the chamber and the wall of the carboy. And the equation for this, as you see in the bottom of the left, is Q, the amount of heat, is equal to the heat transfer coefficient times the area times the delta T. Now, in an upright, it is what we call free convection. There's not a lot of air being moved. And so that heat transfer coefficient, which you can see in the bottom right in the constants, that's around 10 watts per meter squared degrees Celsius, typically for free convection. Now in the FARRAR machine, in a blast freezer, you have forced air, you have a blower blowing it. And when that happens, the heat transfer coefficient goes up by at least a factor of 2, and it can be as high as a factor of 10 higher. So just to be conservative, I've used a factor of 2 here. And so in forced hot air, with forced cold air, you can take out 200 watts. So that's how much heat you would want to take out to freeze this to transfer heat as quickly and as efficiently as possible. So in the bottom left, we're going to compare this back to the two freezers. So in the best case at 85%, or at 65%, remember we have 85 watts of this buffering capacity. And so at 85 watts, you're really only at 85% of that required for maximum heat transfer from one carboy. And so what would happen is the machine would run as hard as it could. It wouldn't be able to reach -80, and it would sit there at above -80 until eventually the ice starts to form and the heat transfer goes down, and the chamber will eventually come down to -80. Now, if you look at the Model 4100 rate chamber by FARRAR with its 1600 watts of buffer, that is sufficient to remove heat from 8 carboys. So it's 8 carboys versus 1, and not only is it 8 times as many, but because it's this convective heat transfer, it does it at twice the rate. Again, that's 16 to 18 times, right, the refrigeration capacity here. So this is really the math I was looking for. We did the math and we found it. And we can see now the difference between a standard ULT freezer and a custom design freezer designed for freezing bulk drug substance and liquid in general. So with this, so next. So what, right? It takes longer. That may or may not be an issue, but are there other issues? And the answer is clearly yes, as we'll explain now, and I'll hand it back over to Sylvain to go over that.
Yeah, thank you, Jeff. So again, looking at this slide, when you look at a ULT freezer, some of you might say, okay, so what if it takes long to freeze? And yeah, I believe the math and I believe the data that you just provided. So yeah, I agree, it's slow. But, you know, just to the point where it's slow, but it's slow meaning it's days instead of hours to freeze product. And what that means for ULT is, the ULT freezer is, it's what the freezer was designed to do that will come back to haunt your operation. Meaning, so you're using the freezer to freeze product, it's running all the time, you're creating more stress on the compressor, and now we eventually are shortening the expected life of the freezer. But let's take a closer look at that. Next slide, please. So on the standard ULT, this is what we call, here's what could go wrong, right? So typically, what's critical for -80 cold wall freezers or the ULT freezers, one of the top thing is the poor routine maintenance. So what happens is if you ignore the ice buildup on the door gasket, well, that actually can drastically increase the heat load on the compressor. So keep in mind that the ice buildup on the door gasket creates a pathway for air to enter between the freezer door and the gasket, or the freezer opening in the gasket. So this translates to compressor running longer, or the worst case is running continuously. And this will greatly reduce the life expectancy of the ULT freezer. The other point is freezer construction failure. Although it's uncommon, but ULT freezers, I mean, they use insulation and they typically use VIP, vacuum insulated panel. So there's a potential that the vacuum insulated panel can degrade over time, or could have been damaged during shipping or when the freezer is moved. So if you lose one of the VIP panel, so this actually increases the heat load for the compressor. So when a VIP fails, it's very difficult to determine the type of failure, and unfortunately, with a faulty VIP panel, this cannot be replaced on a ULT freezer. So again, a failure of a VIP panel will will create a longer compressor cycle time, or again, probably continuous operation and then failure of the freezer. And one of the things that I like to list there is the compressor overheat. and because it gets overworked. So loading warm product in the freezer, if you recall at the beginning of the presentation, we talked about the freezer itself is meant for long-term storage. The freezer itself is great for holding already frozen product at -80. It certainly can freeze a couple of 2 ml vials, but on the larger, I'm going to say bulk product, 10-liter carboy, it's not designed, the ULT freezer is not designed to remove that large amount of energy. And you can imagine the freezer taking days to freeze down a 10-liter carboy, and the amount of heat generated from the compressor continuously running. So again, reducing the compressor life and eventually having a compressor failure. But also important, and I'm going to get techie on you, but these compressors are, although you have a condenser, that's to remove the heat from the refrigerant itself on the high side, but the compressor requires cold refrigerant to maintain compressor the integrity of the internal parts. So these parts need to be cooled. So you can imagine if a compressor is running constantly for days, it's not getting the cold refrigerant that it needs to cool the windings and cool the internal parts of the compressor. So no cool refrigerant means that the compressor will eventually fail because of overheating. And then we get into what's called like the burnout of the oil, and then you get into oil becoming acid, and then it's catastrophic failure. So, you know, people might say, well, why does it matter? So again, overworked compressor is soon to be a burned out one, leading to premature failure. And this is the reason why ULT manuals, manufacturers list in their manuals that loading freezer with warm product, large amount of warm product, will void the warranty. Next slide, please. So when we look at closer at the 4000 series control rate chamber, again, like Jim mentioned, this is a chamber. It's basically the same size as your standard freezer, but because there's, as you can see from the inside, there's duct sheets where we need to circulate the air. So the chamber has a payload of approximately 23 cubic foot or 651 liter. And it is a purpose-built forced air convection cooling. As Jeff mentioned, it's also known as a blast freezer. So it's designed and engineered to remove large amount of heat without putting stress on the compressor, because as Jeff mentioned, and we'll get that into the next slide, it's about the size of the components that are inside, meaning horsepower, the ability to remove the energy, designing what we call a balanced system, because you have to keep in mind that when you're operating a freezer at higher temperature, especially a low temperature freezer, the more stressful part is when you go from ambient down to -80. And typically manufacturers don't want to see that happening too many times, even if you say, I'm going to warm up my freezer and then I'm going to pull it back down again, because it's a lot of stress on the freezer. But on the purpose-built freezer, it's what we call, it's a balanced system. Everything is calculated to work even in the higher temperature. And to get into, I'm going to call it, to go into the weeds, the technical weeds of that is, this is where you get into, on the balanced system, am I running the proper compression ratio, and am I creating more problems for the compressor? So without getting into too much detail, this is why the control rate freezer is the better solution for pulling down large mass of product. And next, please. Next slide, please. So when we look at the purpose built for bioprocessing, again, we're talking about a high output refrigeration system that is equipped with a 5 horsepower high stage compressor and 3.5 horsepower for the low stage. So again, the rate chamber was designed and engineered for removing large amount of heat, of energy. Also keep in mind, unlike -80 cold wall freezer, the rate chamber is equipped with a large surface fin type evaporator coil That includes a blower motor. Jeff mentioned, the energy from the blower motor that's taken into consideration for the watts of energy. Well, that blower motor is capable of performing 60 air exchange per minute within the chamber. So this 23 cubic foot chamber, 651 liter chamber, the air is being recycled 60 times within 1 minute. And that means that speaks volumes. So it's designed to remove the heat from the warm product at more than double the efficiency of a standard ULT freezer, which uses passive convection to remove the heat. So the unit is equipped also, just to get into the granular of this freezer. So it's equipped with an electronic expansion valve. So again, for those technical people, that's it's called an EEV, electronic expansion valve, very similar to a thermostatic expansion valve. And that's the ability to work and generate the cooling requirement versus a ULT freezer, which uses a capillary tube. And that means that the same amount of refrigerant will always be delivered to the evaporator. But again, the thermostatic expansion valve automatically adjusts to flow the right refrigerant based on the heat load inside the product. So if you place a bottle inside the freezer or 100 bottles inside the control rate chamber, the correct amount of refrigerant is automatically distributed within the evaporator coil and to be able to remove the heat. And this is key to be able to, again, remove the energy that's inside the bottle, which is water or the product. So again, to meet the freezing requirement outlined in the control rate chambers as freezing profiles that you can select. And while you can set it for -80, and it goes into its freezing process, we generally keep the temperature uniformity of plus or minus 2 degrees C, and that's, we're talking air temperature. So speaking on profiles, the freezer has two what we call factory preset profiles, and those are easy to set up. So the factory preset, you basically press start and it'll start the freezing process. But you can certainly, if you would like, create your own profile where you would choose to start at plus 20, come down to, for example, 0 degrees C, and hold at 0 degrees C for a period of time, or hold at -20 for a period of time. So you can literally make changes or select different freezing profile within the rate chamber. And again, this is on the rate chamber, the one we're talking about with the user interface. So it's the touch screen. And again, we're talking about a control rate chamber that has the ability to remove a lot of energy. You can preset the controls to go how fast, to decide how fast you want to get to the target temperature. But again, there's also a preset profile where you could use it for thaw. And this is completely different than a ULT freezer. So now that your product is frozen to -80, so there's what's called like DP and DS, right? Drug product and drug substance. And typically on the drug product, on the drug substance part, this is where you will need to thaw the product. So you need to go from -80 to plus 4 degrees C or plus 20 degrees C, depending on your process. And it's more like a water bath, where you take the cardboard and you would sit it in the water bath. But the advantage of the control rate chamber during a thaw process is it enables you to control and maintain a specific temperature. So we've seen in the past where customer will say, I want to be able to go from -80 and hold 4 degrees C. And that process may happen on a Friday, and I want to hold 4 degrees C over the weekend, so our engineers are ready to move on to the next process on Monday. So the control rate chamber has the ability to control and maintain specific temperature for a period of time. Next slide, please. So here we're looking at the value, I'm going to say the value proposition for the forced air versus convection. And when you look at the information here, the chart here summarizes the key features of freezing and storing material. So the green indicates the best and most applicable solution, while the yellow mean it could be able to meet, but maybe not ideal, and the red mean it's not capable of meeting the requirement. So, highlight temperature uniformity of a ULT when it's trying to remove heat from the material. It likely falls far outside the acceptable range. Unless you are freezing, again, small amounts of material, such as a handful of 2 ml vials, therefore you will not have the cooling capacity to freeze and maintain storage temperature in the freezer if you had larger containers like the 10-meter cardboard. So the other thing is when you compare the freezers on the forced air convection freezers, also known as a blast freezer, it's again, the process is repeatable. So from one day to another, you can literally recreate the same process, but there are some drawbacks to purpose-built material freezer. It's not designed to freeze and hold product temperature for a long period of time. So it's not a ULT freezer. So you can freeze a product and hold the temperature for some time. So as an example, you freeze down to -80 and you want to hold -80 for 2 or 3 weeks. It's possible, but again, we generally recommend after each freeze process that you go through what we call a defrost cycle, and then so from there to properly clean and remove all the ice that's inside the freezer, because you have to remember there's a lot of energy inside the freezer. Once you freeze and then you unload and you open the door, all that condensation turns the frozen part, which is the snow and ice, will turn into water, and it's wise to clean the freezer after that. So if you have specific profile to run, such as drop and hold in a certain temperature or changing temperature freezer rates based on temperature, rate chamber is the proper or the qualified unit to use. And again, feel free to contact us for more information to understand how you can program a freezer to fit your need. Next slide, please. So now we're getting into the right tool for the right job. So I've told you about the ULT freezer and what they were designed to do, right? It's to keep frozen product frozen. But again, ULT freezers were not designed to freeze product as it significantly increases the refrigeration or the compressor, right? The runtime of the compressor. So in the same vein, if you have a frozen product, your frozen product doesn't need 1600 watts of available cooling capacity to keep product frozen. So this is where a control rate chamber is not meant to be used as a long-term freezer, and a ULT freezer is not meant to be used as a control rate chamber. So let's recap the right tool for the right job. So freezing material. Look for equipment that is purposely built with a large amount of cooling capacity to freeze product and material, and focus on the features that contributes to constant and repeatable result, such as tight air temperature, uniformity, and adherence to freeze-thaw temperature profile. I'll also look for partners that can help you look for a unit that can support multiple container style, like just mentioned earlier, material such as various size cardboard and such. So storing materials, yes, these are standard ULT freezer, but look for units with high reliability. So units that are robust enough to recover from door opening, because that's one of the biggest challenges, right? You open the door, you close the door, and everybody kind of waits and see how fast it's going to recover. And this is where, when you look at our solutions, we do offer, like, for example, like the ULC ultra-low chambers that are specifically designed to, with forced air convection cooling, to pull down the temperature down to -80. So what makes a control rate chamber different? And so the components and the hardware that are inside. So forced air blower that can circulate large amount of air within the cabinet, a large surface fin coil evaporator type. So it's specifically designed to absorb large amount of energy. The rate chamber is available also as an air-cooled or water-cooled. And this is where in the industry you will find that it's challenging to find a ULT freezer water-cooled. And here's another great feature that's not offered. Again, I repeat myself, but the control rate chamber is also designed to freeze product to -80, but also to thaw product. So when we get into the life expectancy of a -80 freezer, I would say it's roughly 7 to 10 years under normal usage, meaning if you use the freezer as a standard storage freezer, right? So long-term storage. However, a ULT ultra-low temperature freezer life expectancy can be greatly reduced if you use it as a control rate freezer or try to use it as a blast freezer. So in that scenario, you can expect a life expectancy of maybe 2 to 5 years or less, unlike a control rate freezer that is purpose-built and its life expectancy is roughly 9 to 10 years. Next slide, please. So in addition to rate freezer, our Trane Technology business can support the whole value chain from research to production, bulk production, freeze and thaw, and then shipping and transport. So on the left side of the slide here, our custom design solution from IR team provides purpose-built room for your specification. Thermo King has autonomous, quickly deployed temporary solution from refrigerated temperature to -70 to quickly support cold storage need without expansion of your facility. We like to call those temporary solution, and they're fully, those can be fully qualified. And on the right is what we call the final fill thaw, freeze, and storage solution that adapts to any process. And Thermo King can supply temp control, temperature, transport, along with last mile anywhere you need to go. So the next slide.
Thanks, Sylvain. Thank you so much, Jeff. Now we've left time for questions from attendees. I'll turn this over to Scott Masella, who will be moderating our Q&A portion.
Thanks, Amy. We have a few questions out there. I'm going to point a few towards Sylvain and Jeff, and I'll take one myself. So the first question I'll push to Sylvain. Are there any other products in their portfolio that would fit for storage? Besides, so the rate chamber freezes products. What do you recommend for storage?
Yes, very good question. And then so the FARRAR Trane ULC, which is an ultra-low chamber, is available as a 190 cubic foot or 5,380 liter. It has full redundancy. So because it's basically engineered with the same, I'm going to say, platform as the blast freezer or the control rate chamber, so it's designed to store product for a long time, for long-term storage, and again, it has full redundancy. So not only on the refrigeration side, but also on the HMI and on the electrical side.
Right, and just to follow up on that, that is a freezer that's like an upright freezer, but it has 8 times the capacity. So much more of an industrial scale, but ready to deploy solution.
Right, and then just to add a little side notes here, so we also, so there's the ULC, ultra low chamber, and we also have what's called a ULCP that was designed for pallets. So that unit is 311 cubic foot of storage or 8,806 liter. And this one can be either to place placements of up to 4 pallets or material handling, which we also offer material handling solutions so you could quickly load and unload the freezer.
That's great. I have a somewhat related question. Pivoting a little bit, can you describe a difference or some of the differences between an LN2 based rate freezer and our mechanical freezer from FARRAR? I think probably I'll direct it to all of us because I think we all have a little bit of experience with each one of those things.
I'll be glad to start out because I have used both. I did a lot of work developing the CryoVault system, and we use both the FARRAR freezer uprights and liquid nitrogen. The liquid nitrogen works really well. It's robust. It's very, very fast. But what amazed me was the amount of liquid nitrogen it took. It really goes through a lot of liquid nitrogen very quickly. And so for any kind of industrial application, you're going to need a very large outdoor liquid nitrogen tank that a tanker truck can come up and refill on a regular basis. So liquid nitrogen blast freezers work well, but they consume a lot of liquid nitrogen.
Yeah, and I'll go next. So in my technical experience throughout the years, again, the investment is high, like Jeff mentioned, because of the large liquid nitrogen tank. Because keep in mind, when you run a liquid nitrogen tank, the distance from the liquid nitrogen tank to the unit itself, you literally have what's called like a solenoid valve that has to maintain liquid present at the time or at the point of injection, and that vacuum insulated jacketed line is very expensive. So therefore, the investment is quite high for that type of units. And there's also the oxygen depletion and everything else that goes along this on the safety issues.
The safety issue, people don't realize the largest industrial killer is nitrogen because of asphyxiation. So yes, you absolutely have to have oxygen sensors in the room and the associated safety using nitrogen.
Yeah, thanks. There's not too much that I could add beyond what you guys just did, other than it usually comes down to pure speed.
Right. It is fast. It's very fast.
The next question is about how long can the rate chamber hold frozen product, and what would you do with it afterwards? And related to that, any issues with defrost during the cycles as well? I'll direct the first part to Sylvain.
Okay, so on the technical side, on the rate chamber, yes, you can, let's say, have a profile that you pull down to, let's say, -80, and you can hold -80 for a couple of weeks, 2.5, 3 weeks. But there's one key here: as long as you do not open the door. And the reason for that is this: each time you're going to open the door, now you're inducing moisture. And again, our system is a convection cooling, it's got evaporator coil, right? So each time you open the door, what happens is then moisture will collect on the coil, it'll collect on the surfaces, and now it's going to create more problem. More, I'm going to say, icing on the coil, which reduces the overall capability to maintain proper temperature inside the chamber. So in summary, yes, you can up to 3 weeks, and then after that, you would literally just open the door, empty the cabinet of the content, and then and what we would do is you go what's called a defrost process, and then you wipe down the interior of the chamber and get ready for the next process, pull down temperature.
Right, that's my experience as well. We froze tremendous volumes of fermentation paste, and we used a blast freezer for freezing it. And then after a couple of days, when it was all frozen, a crew would come in with a transport box and move it from the blast freezer to a long-term storage facility. And that could be uprights, that could be the FARRAR solution, it could be a very expensive, large -80 freezer. But that is the process I'm used to. You freeze it in a blast freezer, and then you move it in storage in a storage facility.
Yeah, and then there's just one more point to add here. From my experience in working with customers, some customers believe that you precondition the -80 before you place your bottles inside, and that's not required because our freezers is very dynamic, right? So you open the door, you place the product at room temperature, and the freezer will be able to pull the temperature down to your set point of -80. So preconditioning is not a requirement.
Great. Another related question to the rate chamber and also forced air convection in general. Is there any concern around reliability for the fan motor or the blower motor for our forced convection units? I can start with that one,
Okay.
if you like. And the answer to that is no. There are no reliability. Well, any moving part would have a reliability concern at some point. We architected this design in this blower motor to be oversized for the application. If you're familiar with factors of safety, there's a large factor of safety on this blower motor so that it's designed, it's purpose built for this particular process. We didn't just use a standard small fan for that. Any comments, Jeff or Sylvain, that you want to add to that?
Well, I would say that, again, it's a over-engineered sometimes. I like to say that, but it's our units is our engineers spend a lot of time, and it's all about heat breaks, meaning where you make sure that cold or moisture is not induced inside the chamber via the shaft of the motor. So all that was taken in consideration during the design and the engineering of the chamber. So yeah, it's I would say that the blower motor would be one of the last thing I would be concerned about a failure with the control rate chamber.
Yes, and I agree. We all know upright freezers tend to break down. They're not real reliable. Blowers have been around for a long time. This is not a really large blower. And so it is a well-known piece of equipment in the industry. It is robust. And if it did fail, it's relatively simple to fix, unlike a -80 compressor, which is a far more complex piece of equipment.
And just a little more techie information here. So it's a centrifugal type blower wheel. So therefore it moves a lot of energy, but by doing so, you don't collect ice over the motor itself, the shaft and so forth.
That's helpful. For Jeff, how do I get help in designing a freeze thaw process that best fits the needs that I have?
We'd be glad to do that. So feel free to reach out after this webinar. We will have contact information, and we'll be very happy to work with you and your particular process.
Scott, you're on.
We have one more question. This one's a little interesting one, but it kind of goes back to some of the roots that I've had, which is, what about freezers that use engines instead of compressors? How do they compare? When you look at our study and the thermodynamic equations that Jeff presented, I'll start, and then I think Jeff or Sylvain, feel free to jump in afterwards. But in a nutshell, freezers that use Stirling engines, such as Stirling Ultra Cold, will have the same capabilities to freeze. I'm sorry, have the same capabilities to maintain a cold cabinet that a standard cascade compressor system would. The Stirling engine sized specifically to remove cabinet heat from the cabinet, the door, and the door gasket. The major difference is the Stirling engine is capable of continuous operation, so it can remove heat from product as well as remove cabinet heat. The major downside is it's very, very, very slow. So what you might be used to freezing and out of your standard cascade compressor storage freezer in, let's say, 4 or 5 days, that you can expect something similar with the Stirling as well. Anything you want to add, Jeff or Sylvain?
Yeah, I think you summed it up well, right? The duty factor that we just discussed of 65 to 75%, it's the same in most upright freezers, right? So the equations we showed, the examples we showed are the same as far as how long it takes.
Yeah, and on the technical side of things, the one thing that you'll notice, I mean, from a cold wall freezer, right, it's the overall temperature uniformity within the cabinet. So this is where, for your process, when you're placing all your bottles, whether they're 1 liter bottles or 10 liter carboys, the difference from the bottom to the top, I mean, you can expect to see a variation of +6 to +9 degrees. And unlike a control rate chamber, because now we're circulating air, the uniformity is much better, where you could be at ±2 or better. So this is where during your qualification process, you may have to do some explaining, right? I mean, especially if the tolerances are higher than what they should be, and your product's supposed to be maintained at ±2 degrees.
Yep. And that's all we have. I'll turn it back to Amy for any conclusion, any comments?
Thanks. Yeah, thank you guys. And we want to thank all of our attendees today for joining the presentation. We will be sending out some helpful resources as well as an opportunity to provide feedback on how relevant you found today's presentation and how we can continue to improve. Have a great rest of the day.
Okay, thanks everybody.